Thank you for joining me for this video. I am Mr. Ish. You are joining me here for what will be slightly an out of the ordinary topic, extending the Maclaurin series to the Taylor series. Essentially, you're working from this direction up towards a Taylor series with a good practical example or two at the end of this video. If you start out with a representation which looks like this, an x and y axis on which you draw this function which looks like f of x. This right here, my x value, I'm representing it right here along this y-axis, is x equals 0. There's a specific point over here. What would that point be? It would be f of x, but literally what would it be? A function is something which takes an input. You're taking this input, you're looking here at f of 0 because the 0 is going right over here. When you're looking here at Maclaurin series, you're looking at something which looks like this, and you know it to be the case. Bring that into this form. Actually, bring this into this form. When I'm looking at this point over here, how does everything play out with the expansion of this function at that specific point? It'll play out exactly as I'll show you. You will have the original function. Remember, the zero order derivative is the original function. I'm not even gonna bother writing x to the power of n divided by 0 factorial because that's meaningless. Your next item will be this. The first order derivative with the 0 coming in, 1, and then x to the power of 1. Then the next is the second order derivative with the 0 coming in, which is here the x value here of 0 over 2 factorial, which is this, and x squared. And then the other item is the third order derivative, and then you have x cubed over 3 factorial, which I'll write as that. And then you can say the fourth item here, the fourth order derivative, x to the power of 4 divided by 4 factorial. You see how everything is built up? Now consider this. You extend a certain number of points away or a value away at h. And this point becomes, if this right here, if x was 0, you're h units away, you're 0 plus h, you're h units away. This point here becomes f of h. How do you incorporate an expansion with regards to this point over here at this value over here? How do you do that? You look at exactly what you have. This right here was equal to all of this. F of x was equal to all of this, except our f of x was really f of 0 because we were centered here at x equals 0. The only thing that's changed here, instead of a 0, we're now looking at an h. Instead of looking at this, we're looking at that. Or rather, I should say, instead of looking at that, we are now looking at that. The only thing which changes here is this. X variables here will get replaced by h variables simply because the x value has been replaced by h. Now our expansion for this function here centered now at this point is still f of 0 here as the first term, because you are finding the values here of x and you're putting in h, because f of x is being replaced by f of h. Wherever you have an x variable, the h will fall into it. There's no x variable here, it stays as is, but there's an x variable here. You'll have that, and then h over 1. Then the next item is this, h squared over 2 factorial, and now you're beginning to see the idea. Here you have h cubed over 3 factorial, and then here you have a fourth order derivative. You have h4 over 4 factorial. You see how we've evolved, and I should say this right here, f of x was f of h. It would make it a little more clear. F of x originally around 0 is that. F of x now at h is equal to this. What happens now if I shift everything away? And not only do I shift this origination point which anchored everything, but I shift this and all of these things shift in this direction. What becomes our representation? I'll tell you what it becomes. This point over here which was originally here will become right over here. This point or line which was originally here will become right over here. This was x, this is x plus h. If this right here was f of x, this here is f of x plus h. Do you see what I'm doing? The original function is still the same. This original curve is still the same. Originally we were right here and I went h units away. But now I'm shifting everything. This original anchor point and the secondary point, it has come over here, and then the other point has come over here. Hence we have x plus h, and here we can say we have 0. Now what would the series be if I wanted to incorporate this into the series? I'll tell you what it would be. Your series expansion for something which looks like this, or x plus h, would be this. Remember, at all instances, don't forget this, the Maclaurin series expresses a function in terms of its derivative, so keep that in mind. If a Maclaurin series expresses a function in terms of its derivative, the Taylor series does the exact same thing, except your function is not anchored at the point the Maclaurin series is, it's anchored at another point. Anyhow, And anchoring and centering are the same synonymous terms. How would you incorporate this into what you're seeing over here? If f of x was originally viewed here as f of 0, and then we viewed as f of h, then now we're looking at this. What are we really looking at? We're really looking at f of x. This right here, f of x right here, my f of x, and everything will build off after that in exactly no other way other than what I'm showing you. You will have now the first order derivative, and in places of these right here x's, you'll put your h's. Here in the bottom you'll still put your factorials, and then you'll have this. You'll have h squared over 2 factorial plus, I'll come down here, your third order derivative, you'll have x. You'll have h cubed over 3 factorial, and last one, the fourth order derivative, you'll have x, you'll have h to the power of 4 over 4 factorial, and on and on. Now look at the difference. This is f of x around 0, it looks like that. This is f of h, it looks like that. F of x plus h, it looks like this. This right here is what I'm trying to get to for my application questions, because you can utilize this template for something very important or for practical applications. This specific template now represents a Taylor series which was adapted from the Maclaurin series. This specific template is what I need to now put on the top as my template for the two practical applications I want to show you. I'll put them up, then we'll look at those two items. Now I've put everything over here, but I've gotten rid of the factorials. Everything else is the same. I've just calculated those factorials, so I don't have anything with that designation. If I want to evaluate this, how would I go about doing it? Sine 75 degrees. Utilizing what I have presented here as a Taylor series template. It's slightly out of the ordinary Taylor series template. How would you do this? You're thinking about something like this. It's coming from sine 30 and sine 45. It looks very much like an x plus h. What is my x value? What is my h? Remember, when you do the expansions of trigonometric functions, everything must always be in the radian mode or AD mode. My x value here is a 30. My h value here is a 45, but you must present it in the form of a radian, not as a degree. That right there is my true x and h value, pi over 6 and pi over 4. But you can do this calculation here on your calculator on the DEG mode and present it and hold it. 75 sine on the DEG mode, I have 0.9659. That's the value I want to try to get close to, 0.9659, and I can come close to this value utilizing this template right over here. And let's do it. If I want to be a little careful, I can put a few more digits. Let's look at everything here. F of x plus h with regards to this sine function is really us looking at f of here, pi over 6 plus pi over 4, but with regards to the sine. And it's more than just that. I still have these derivatives. I have a 0 order, first order, second order, and we have to come up with that. The 0 order sine is just a sine. The first order sine is a cosine. The second order sine is basically a minus sine. And I'm going up to the fourth. The third order is going to be a minus cosine, and the fourth order will be a positive sine. I have this template laid out. I have these x and h values which will come in. My f of x will be what? Over here. It'll be basically just sine of whatever the x value here. This f of x right here is my function. My function is a sine function. Therefore, f of x is the sine of your x value, which is 30 degrees or pi over 6. My first item will be sine of pi over 6. Remember, it has to be in radian mode. My next item, the first order derivative, which is right here, will be cosine of the x value, which you know here is a pi over 6, times the h value, which is pi over 4. All over 1, meaningless. My next item is a minus sign, and I'll do minus sign. And here, you know, I forgot these variables, but it's alright. Minus sign. In all instances, x is a pi over 6. In all instances, h is a pi over 4, but here it's a pi over 4 square. We have a pi over 4 square over 2. This next item is a minus cosine of x, which is a pi over 6. Again, x is always pi over 6, h is always pi over 4, but here I have a cube. It'll be pi over 4 cube over 6. And let's do the last item. It's a positive sign pi over 6. Then you have h to the 4, which is a pi over 4 to the power of 4 divided by 24. You have to compute this. You compute all of this, you take it to a good number of n items, it should come here. If you don't put enough of these n values, it'll be far from here. But if you do enough of these, Going further out to a higher n value, you'll be closer to that. So now what we have is the arduous task of doing this entire computation on the radian mode. This right here will be a 0.5, sine of 30 or sine of pi over 6. Either radian degree mode is always a 0.5. Let's do this. And then we'll start adding these numbers together. Pi divided by 6 cosine times pi divided by 4. I'm getting a 0.680174. I'll add that in. 0.680177. Let's work over here. I'm going to work from the right towards the left. Pi divided by 4, square it, divided by 2 times 0.5, which is the sine value. It's minus 0.1542. Minus 0.154212. Let's come over here and we'll bring the value right here. We'll work again from the right towards the left. We'll do pi divided by 4 and we'll cube it. Then we'll divide it by 6. I'm saving this value. I'm going to do pi divided by 6, the cosine of that, multiply that with that saved value, and have a minus value here, minus 0.0699. Last one, we'll do that again. That computation from the left towards the right. I have pi divided by 4 to the exponent 4 divided by 24 multiplied by sine of 30 degrees, which is sine pi over 6, which is 0.5. I get 0.007927. Now we have to add up all of these numbers and see what we get. We should get a number close to this. If you do enough n values, you'll be very close to it. If you do minimum number of n values, you'll be a little far away. I'm working from this last value towards the first value, minus 0.069927 minus 0.154212 plus 0.680177 plus 0.5. I'm getting 0.96396. And I'm going to put it right out here for you, 0.9639628. Are we far away? Well, I'm close up to the first two digits. After that, I'm off. But that's fine. I only did up to n equals 4. If I'd done a bunch of more n values, I'd be closer. But you see how this technique is quite different than what you've seen in the previous videos. We centered those around the Maclaurin series for the sine function. Here we're centering around Taylor series, but utilizing this template. Let's look at one more question. It'll be just a good confidence builder for this particular out of the ordinary exercise we're doing, and that'll be it for this video. Let our function be this. We have to look at it in this form. Either it can be a sum or it can be a difference. I'll do a difference. It'll be 45 minus 30. 45 minus 30 cosine is equal to cosine 15. Let's get the value and plug it out on the DEG mode. 15 cosine, I'm getting 0.96592. 0.96595. Now here's my x value. My x value here is a 45, which is pi over 4. My h value here is a 30, which is pi over 6, but it must be a minus pi over 6 because there's a minus attached to it, so don't forget the minus. Come up with your derivatives. The zero order derivative is just basically your original function. Your first order derivative is minus sine x. Your second order derivative is going to be minus cosine x. Your third order derivative is going to be sine x. Your fourth order derivative is going to be a cosine x, and you'll shuffle back to the original function as you see it. These will come right here into that template. F of x. What's f of x? It's your original function, cosine, but what exactly is the x value? It's pi over 4. Let's come over here. What's your first order derivative? It's a minus sine x. So let's bring in a minus. Minus sine x. X here is a pi over 4. And h over here is a minus pi over 6. See, this minus will convert that into a positive. My next item is a minus. Then I have a cosine. In all instances, x is a pi over 4. H is a minus pi over 6. Here you have a pi over 4. And then here you have h, minus pi over 6 square over 2. The next item is a sine x. I have a sine, but x here is always pi over 4. Then I have an h value, minus pi over 6 cube over 6. Then let's do the last one right here. We have here cosine. X here is always pi over 4. And then we have minus pi over 6. Remember, don't forget this minus. It's coming from right here. Because here the template is for x plus h. Here the plus h is really a minus. The minus comes with it. This is to the power 4 divided by 24. You have to do this entire computation. You'll end up right over here. So your shortcut here is whether it's the RAD mode or the degree mode, sine and cosine are always 0.707. And we can keep it to just that. You don't have to waste time doing that calculation. Do pi divided by 4. and do the sine or the cosine, you'll have 0.7071. We'll keep that. Now let's compute this. You'll have pi divided by 6 times 0.7071, but we have a minus becoming a positive. It's 0.3702366. Let's come over here. That's a minus. We'll do everything from the right towards the left. We'll do pi divided by 6. We'll square it. We'll divide it by the 2. And then we'll multiply it by 0.7071 negative. And we're getting a minus 0.0969. Let's come up to this value and let's do that. Work from the right to the left. Pi divided by 6, cube it. It's going to be a minus value because it's cube of a negative value. Divided by 6, multiplied by 0.7071. I'm getting a minus 0.0169. Lastly, this one right here. It's going to be a positive value. We'll do pi divided by 6 exponent 4. That negative is meaningless in an even exponent. Divided by 24 times 0.7071. I'm getting 0.002144. Let's add up all of these numbers and we should have a value close to that. Plus 0.016917, which was a negative value, plus 0.0969277, which was a negative value, plus 0.3702366, plus 0.7071. I'm getting 0.9657. These are all the values I added. When I add them all, I get this 0.965706334, and we can compare. Here I have 0.965, here I have 0.965, then I differ from there onwards. But you can see how now we're utilizing the Taylor series for these approximations. In some of the previous videos we were using the Maclaurin series, but we converted a Maclaurin series concept into a Taylor series concept. We extended the Maclaurin series to the Taylor series, and we came up with this entire template expansion scheme, which we are now applying to these trigonometric functions in the RAD mode of your calculator, and we're coming up with these values, and they're not bad values. And that right there is the end of this video. Thank you for watching.